Last time we talked about exponential functions generally, and we said that an exponential function, we typically write it in the form y equals a times b to the x, right? Where a is going to be your initial amount, or your y-intercept. That's one way to think about it. And then b is going to be your constant multiplier. Or sometimes we call it the constant ratio. In other words, that's the number that you're multiplying over and over again. And we saw that if that b is bigger than 1, are we going to have growth or decay? If b is larger than 1, like if your multiplier is something like 2 or 10 or 7 halves, any number that's bigger than 1, then we have growth. But if that b value or that constant multiplier is smaller than 1, if it's like 1/2 or 1/3 or 2/3 or anything that's smaller than 1, then we'll have decay. So it's really all about like how far away that number is from 1. Is it above 1 or below 1? And that's going to sort of control the overall behavior of the graph. So an exponential. So let's start with growth. Okay, so growth occurs when a quantity increases by the same factor over equal intervals of time. So what we're going to do is kind of break down this y equals a times b to the x into like two separate equations, one to represent growth and one to represent decay. So for growth, we're going to write the function in this form, y equals a. So I'm going to let a be what it is. And then instead of writing b, I'm going to write 1 plus r. Okay? In other words, we know that because it's growth, that b value needs to be bigger than 1. So if we figure out, like, well, how much bigger than 1 is it? We can state what the rate of growth is. In other words, if it's like 1.5, we can say, oh, there's 50% growth. If we say that b value is 2, we can say, oh, there's 100% growth, and so forth. So that is your b. Well, we're going to get a lot more detail here, but this r is really what we're going to focus on for today. And then to the x power, or we could say to the t. If we're going to start looking at these word problems, and today's quiz is a little bit of a preview of that. We're going to use t instead of x, but that doesn't really matter.
What is our test? Okay.
All right, so let's break down what all these things mean. Okay, your y, that's your output. That's the final amount that you're going to have in all these word problems. Okay, so like after it's all said and done, after the time has elapsed. Speaking of time, t is going to represent time, typically in years, but it doesn't have to be years. It could be minutes or whatever the context says, but most of the time it's going to be years. A, well, A is just A, what it's been. That is your original amount or your y-intercept. So you've got the original amount and the final amount. The R is going to be the rate of growth or the growth rate. Now, what we're going to see in a second is that we can sort of change this equation to make it decay, and then we would call that the rate of decay. So we're going to use the same variable in both of those forms. So what you need to know is that the r represents either the rate of growth or the rate of decay, depending on what the equation looks like. All right, so let's look at a couple of these. So number one, we've got this function. There's no context built around it, but we want to know first what's the initial amount and what is the rate of growth. So what's the initial amount? 25. And what's the r value here? 0.5. So when we talk about rate of growth, though, we are typically going to talk about it as a percent, like a percent growth. Like it's growing at 50%. It's growing at 100%. Growing at 75, whatever. So what is 0.5 as a percent? Yeah, 50%, good. So say there's 50% growth. All of these are going to be growth, by the way, so far. Number 2, what's the initial amount?
115.
Yeah, 115, right? And then the R value, you're looking in the right place, that's good. So the R value here is 0.04. What's 0.04 as a percent? Yeah, so that's 4% growth. Number 3, this looks like it might be a money problem, right? So we got our initial amount is 2,000. Now I want you to be careful here because notice on this problem, the 1 plus R has like already been combined, okay? So I don't see like 1 plus something, I just see 1.62. So what is the R value here? 62%, good. Because it's 1, this number right here is 1 plus 0.62. And we could start to write functions that model growth, okay? Quite often when we talk about these exponential growth or decay functions, we're talking about the value of things. You know, like if you buy a car, it's going to depreciate in value typically exponentially. You'll have an exponential decay. Or if you take out a loan, how much you owe is going to go down over time as you pay it off. Or on the flip side, if you make an investment, that will typically have an exponential growth. Okay, so it'll be like becoming more and more valuable over time. Like a house is like one of those weird things that actually increases in value over time. Okay, so number 4, the value of a $200,000 house increases by. Is it 3? Did anybody get a clean copy here?
I got
3%. Yeah, mine got the hole right through there. 3% each year. Okay, so we're going to write the equation. Y equals 200,000 times 1 plus what? 0.03, right? So you can leave it like this, or you could combine it. Either way is fine. What I mean by that is if you want to write it like 1.03, that's okay too. That's actually probably better. Yes, sir.
Is it always assumed to be 1 plus something?
When it's growth, yes. This next problem says the population of 200 bacteria increases by 23% per hour. All right, so what's the initial amount? 200. And then so we have 1 plus 23%. That's 0.23. So once we combine those, we get 200 times 1.23 to the power of t. And if you use x, that's fine. I mean, that letter is not, it doesn't necessarily need to be t. It could be x. Number 6. In 2005, there were 100 rabbits in Polygon Park. The population increased 11% each year. Write an exponential growth function that represents the population t years after 2005. So this is going to happen pretty frequently in these word problems, is that they're going to set like a date or like a year that is going to be like the beginning of the situation. And so what that means is that year represents t equals 0. Or I'm sorry, t equals 0 represents that year. So in this case, 2005 is sort of our starting point. 2005 is what t equals 0 means. All right? In other words, no years have passed since 2005. So after I write my equation and I want to say, okay, well, how many rabbits are there in 2010? What would I plug into t? Not 10, 5, because that's 5 years since 2005. All right, so that can be a little tricky. You want to know what your baseline is, essentially. If this is the beginning, all of the years we're going to be plugging are going to be how many years after that. So let's say, well, let's not actually say anything. Let's do this, and there'll be some problems for us to solve. So write an exponential growth function. Okay, so y equals, what's the initial amount? 100. Okay, so then we have 1 plus our growth rate, 0.11, to the power of t, which is y equals 100 times 1.11 to the power of t. Notice that that multiplier is bigger than 1, so we know it's growth, right? Like that's what you should be thinking about. Okay, so part B says, what will the population be in 2025? So this is sort of, I think, the hard part of this, that you have to decide, okay, well, if I want to know what the population is, I need to plug some number into t, which represents the number of years. So how many years has it been from 2005 to 2025? 20. So when I go to plug that into my x or my t, I'm not actually going to plug in 2025. I'm going to plug in 20. Because 2025 is 20 years after 2005. From there, you're just going to put in your calculator. Okay? And it says round to the nearest whole number. So they've got 100 times 1.11 to the power of 20, and I get roughly 806 rabbits. So I'm going to do a little approximation symbol. If you do these little like squiggly equals, that means approximately. So approximately 806 rabbits. Let's talk exponential decay. What we had said previously was that when you have decay, that constant multiplier needs to be smaller than 1. Okay. So when we come up with this equation, we don't want the rate to make that b value be bigger than 1. We want it to be smaller than 1. And so the decay rate is going to still be the difference between 1 and whatever the number is. So to get there, we're going to say y equals a. So this equation is basically going to be the same, except instead of being 1 plus the rate, we're going to say 1 minus the rate. That will ensure that we get a number less than 1. Because if you do 1 minus something, like that's definitely going to be smaller than 1. Right? Like 1 minus 0.5 or 1 minus 0.75 or whatever the number happens to be. Everything is still the same. Yes, sir? Sure. So all of the variables still mean the same thing. So we can just kind of fill it out quickly here. This is still going to be the final amount. A is still going to be your initial amount. T is still going to be the time. And then the R is still the rate, but when you have exponential decay, we're not going to call it a growth rate or a rate of growth. We're going to call it a rate of decay. So it just takes on a slightly different meaning. So we're going to do basically the same thing that we did with growth for decay. We're going to identify both in these next couple of problems, the initial value and whatever the decay rate is. So for number 7, our initial amount is what? 15. What's the decay rate or the rate of decay? So we don't want to report the b value. I just want the r value. So you kind of get it the same way you got the growth rate. It's this number right here. 40%. Yeah, so it's 40% decay. Number 8. What's the initial amount? Okay, 250. What's the rate of decay? 72%. Oh, not 0.72%, just 72%. And then number 9, we've got our initial amount is 1,000. Now this is where it gets a little tricky. Okay, what we have here is 0.6. I don't have the 1 minus something. This is my b value, but that's not really what it's asking for. It's asking for the r value. So what we have to think about is this number, this b value, since it's smaller than 1, is going to be 1 minus something will equal 0.6. So what does that something have to be? 0.4. Yeah, so r is 0.4. So if r is 0.4, what is the decay rate? 40%, yeah. With growth, it's a little bit more obvious because it'll be something like 1.4, and so you say 40% growth. With decay, it's not as obvious. The value of a $30,000 truck decreases 15% each year. Okay, so we've got y equals, our initial amount is 30,000. Is this growth or decay? Decay. It's saying it's decreasing, so it'll be 1 minus 0.15 to the power of t. So your calculator can come in handy here. You might be able to do it in your head, but maybe not. 1 minus 0.15, what does that come out to be? 0.85? Yeah. Number 11 says the amount of a 25 milligram medication in your bloodstream decreases 60% each hour. That word decreases is what's indicating that we're having exponential decay. If y equals the original amount, the 25 milligrams, times 1 minus the decay rate, which is 60%, so 1 minus 0.6 to the power of t. So what's 1 minus 0.6? What is it? 4, yeah. Number 12 says you drink a beverage with 120 milligrams of caffeine. I could use something like that right now. Yeah? Anyone else yet? Each hour, the caffeine in your system decreases by about 12%. So it's an exponential decay. That makes sense, right? Drink your cup of coffee or soda or your energy drink or whatever. You feel that caffeine rush, and then it just sort of slowly kind of drifts away, right? That's basically what's happening here. Write an exponential decay function that represents the amount of caffeine t hours after you drink the beverage. So in this case, our t is in hours, not years. Most of the time it'll be years, but in this case it's hours. So let's write our equation. Y equals our initial amount, which is 120, times 1 minus our decay rate, which is 0.12 to the power of x, or t. That doesn't really matter. We'll go with t. So what is 1 minus 0.12? 0.88, okay, so we got 120 times 0.88 to the power of t, and that will help us answer the next question, which is how much caffeine is in your system after 4 hours? So where are we going to put this 4? And the t, right? So y equals 120 times 0.88 to the 4th power. This is something we're going to just plug into the calculator. So I get approximately 72 milligrams. One last thing, we're going to talk about compound interest. So this is just going to be a slightly more complicated version of what we did. Okay? So first things first, you will not have to memorize this equation. Okay, so don't spend your time trying to memorize this equation. If you're gonna like memorize anything, memorize what all the variables mean. Know what P stands for, R, N, T. Okay, compound interest is the interest that's earned on principal. So, if you, for instance, let's say you take out a loan to buy a car, right? Let's say the car costs $20,000, and you don't have $20,000 to buy the car. That'd be a lot of cash on hand, right? Like, you probably don't have that much. So what most people do is they take out a loan to buy the car, meaning you tell the bank, hey, you buy this car for me and I'll pay you back a little bit every month. Sounds like a good deal, right? You spend like 4 or 5 years to pay it off. So what is the bank's incentive to do that for you, to front you that money? Like, why would they do that?
Because they can collect interest on your money.
They will collect interest. Basically, the way they make money is by charging interest on money you borrow. So in other words, every month you pay a little bit extra. You say, okay, well, I owed you like, $100 for this month, but I have to pay like an extra $10 in interest, just to kind of throw some easy numbers out there. And so that's how the banks make money, right? Like, basically they collect on interest. So what this little formula will do for you is tell you like how much an investment will be worth, or on the flip side, how much do you actually spend on a house. So this formula has a bunch of variables. So let's define all these variables, okay? So P stands for principal. Now I'm not talking about Mr. Butler here. When we start talking about a loan or an investment, the principal is the original amount. Okay, so that's like, how much money did you borrow? Or how much money did you originally invest? The R is the interest rate. The N is the number of times interest is compounded. Now, what I mean by that is, so interest can compound or basically like be applied in different intervals. You might have a loan where the interest is compounded yearly, where just once a year they add on interest. Or it might be they add on interest once a month. So if the interest is added monthly, then the end value would be 12 times in a year, right? If it's added yearly, the end value would be 1. So I want to write down just a couple of common words that you'll see so you'll know what the end value is, because typically the end value is not going to be a number that you just circle in the problem. You'll have to figure out what it is. So for n, the number of times interest is compounded per year. If it's yearly, n is 1. Quarterly, what if it's quarterly? What do you think n is? So how many quarters are there in a year? 4. So you'll compound it 4 times. If I say that it's compounded monthly, what would the end value be? 12, right, and so on. So that's how you're going to kind of figure out, what the end value should be. Finally, T is the number of years, time. Okay, so you don't have to memorize that equation. You just have to know what all the variables are. And ultimately, these kind of problems are just strictly calculator problems. As long as you can put the numbers in the right place and type them in your calculator, you'll get the right answer for the most part. Okay, so let's look at number 13. It says 3,000. Write a function that represents the situation. We're going to deposit $3,000 that earns 6% annual interest that's compounded quarterly. Okay, so let's like break down what all these numbers are, like so we know where we're going to put them all. If the initial deposit is $3,000, what variable, like where am I going to stick that? Like what variable does that represent? P, that's the principal, right? So that's my P. The 6% annual interest, which variable is that? R. And since it's compounded quarterly, what is the end value? 4. So that's the tricky part of it, is that end value will not be explicitly stated. It'll say quarterly or annually or weekly or something like that. So let's write the equation. Y equals 3,000 times 1 plus 0.06 over 4 to the power of 4t. There's your equation. Yeah. So number 14, we've got a $5,000 deposit. That's my P. That's my principal. It earns 7.2% annual interest. That's my interest rate. And it's compounded monthly. If it's compounded monthly, what should the end value be? 12. Good. 12 months in a year. Y equals 5,000 times 1 plus 0.072 over 12 to the power of 12t. Now, both of those problems just had us write the actual function. This next one, we're going to actually do something with it. It says in 2010, you deposited $150 right away. There's my principal. Into an account that earns 5% annual interest. There's my interest rate. It's compounded quarterly, so what's the end value? How many quarters are there in a year? 4. So n is 4. If you did not withdraw or deposit any more money into that account, how much money would you have in the year 2020? So one thing, just a sidebar here, you know, a lot of people think, oh, interest is terrible. Like you just like, but interest can work for you. It works against you if you're the one borrowing money. But if you're the one lending money, if you're making an investment in something, then you actually want a high interest rate because that means you're going to get paid that much extra. Okay. So anyway, we've got y equals 150. That's the amount that we're depositing times 1 plus 0.05 divided by 4 to the 4t. Now, what was our baseline? Like, where does this situation begin? 2010. And we want to know what's the value of this account in 2020. So what should our t value be? How many years have passed? 10. Right? T is going to be 10. So I'm going to plug in 10 right here. Four times 10. So that'll be 40. Right? And now I'm just going to type that entire thing into the calculator. The entire expression. Just exactly how it looks. I'm not even going to try to simplify anything up front.
But doesn't the calculator not do PEMDAS? Doesn't follow PEMDAS?
It absolutely does. Yeah. The calculator will do exactly what you tell it to do. So we're going to just type it in exactly how it looks. Hit enter. And so we get approximately $246.54.